Alright, so it's time for weekly contest 201. I'm starting late again. I tried to figure out the timer thing. It's not working. Change my Python environment variables, whatever. Okay, hope this is better than the bi-weekly contest. Alright, hello. This contest was super epic. And it's not super epic because I solved all of the problems, or actually it is because I solved all the problems. I was going to say it's not because I got a good rank, because I didn't. I got like 1,000th place, which is usually worse than I usually do. Usually worse than I usually do. And no, it's because I managed to solve the fourth problem in the last like 2 minutes or something. And I'll explain more about that later. But first, we're going to go over the first three problems. Problem 1, make the string great. Given a string S of lower and uppercase English letters. A good string is a string which doesn't have two adjacent characters, whereas the left one is a lowercase letter and the right one is the same letter but in uppercase, or vice versa. To make the string good, you have to choose two adjacent characters that make the string bad and remove them. You can keep doing this until the string becomes good. Return the string after making it good. The answer is guaranteed to be unique under the given constraints. Notice that an empty string is also good. Okay, and then it gives a few examples. So basically, we just need to keep removing bad pairs, and then until we don't have any more bad pairs. So over here, we just have a variable to check whether it's bad, and then we loop through the entire string, and to check if two adjacent letters are bad, we just have to make sure one of them is the same letter but in a different case. And we can do that using the ORD method. And this ORD method, basically, it's a way of converting a character to its ASCII integer representation. And basically, if you look at like a chart, so like I might search up ASCII chart. So like here's classic ASCII chart. We look at this and we see all the letters are over here, and they're indexed starting from 65. But the important thing to note is that the lowercase letters are exactly 32 greater than the uppercase letters. So if you can just find the distance between two of these letters, if they're the same letter but at different cases, then their distance has to be 32. So we just make sure that the absolute value of their difference is 32. And then if so, then we know this pair is bad, and then we can remove it over here. And then once there's no more bad letters, no more bad consecutive letters, we can just return the string because it's good. I think the main part of this problem is, first noticing that it's short, because then we can do like n squared or n cubed, and it doesn't really matter. And the second thing to note is that we can use ASCII tables to find the relationship between two letters. Problem 2, find kth bit in nth binary string. Given two positive integers n and k, the binary string Sn is formed as follows. S1 is 0, Si equals Si minus 1 plus 1 plus reverse invert the previous one for I greater than 1. And then reverse basically just reverse the string, and invert replaces zeros with ones and ones with zeros. We can notice that the size of the string grows exponentially because it adds the previous string to a string of the same length as the previous string. So basically it keeps doubling in length, basically. And we note that n is less than or equal to 20, so we wonder, can we simulate this? Well, each operation is going to take at most, so in total there's going to be about 2 to the n operations, because the largest string is 2 to the n, and then we just add all of the ones before. That's going to be about 2 to the n. So since n is 22, the n is about a million. And a million is probably doable. We just have to make sure that we don't go too overboard, because 100 million is about the limit. So over here we just describe an invert function because I don't necessarily want to write it in here. And then yeah, we just simulate it out, adding the previous string, adding a 1, and then inverting the reverse, which is still the same as reversing the inverse. But this is reversing the inverse, right? We're supposed to do that. Yeah, okay. But if you invert the reverse, that's the same thing, because they're not dependent on each other. And after simulating, we just return the kth bit. I'm sure there's a smarter way to do this, but I thought it was doable because 2 to the 20 is only about a million. So I thought simulating was fine, and it worked. So yeah, just brute force this one. Problem 3, maximum number of non-overlapping subarrays with sum equals target. Given an array nums and an integer target, return the maximum number of non-empty, non-overlapping subarrays such that the sum of values in each subarray is equal to target. So I thought this one's like a pretty classic problem, and I thought I'd actually done it before, but maybe not, because I thought it'd appear in a previous Leetcode contest, but apparently not. Okay, so basically this concept is kind of like two-sum, except with range sum queries, and we're going to use prefix sums here. So I might want to draw some things, but okay, so I'm going to pull up a diagram over here. Yeah, basically, okay, my diagrams are mouse drawn, so they're not going to be very good, but okay, so if we have an array and we want to find the sum of this subarray, for example, between a and b, we can take the sum of all the elements up to b and subtract them from subtract the sum of all elements up to a, because that's only going to leave all the elements in here to sum, and that's our answer. So that's how we use prefix sums. But the idea here is to note that if we're looping through the array linearly and we're tracking the prefix sums we've seen so far, if we're at this index b, for example, we want to know if b minus target exists in the prefix sums we've seen so far. And why? Well, if this exists in the prefix sums we've seen so far, then b minus this value is equal to target. And this is important because if we know that, for example, a is equal to this value over here, then we know that the sum between a and b is going to be equal to target. So we just need to make sure that b minus target exists in the previous subarray, and then exists in previous prefix sums. And if so, then we can form a subarray with sum equal to target. And I'll explain why this greedy approach works and why we don't have to consider doing other things. So if we're at this index b, we're going to consider all the prefix sums we've seen so far. There's a few limitations on this. I'll explain that later. But basically, if we find like in the index here that this works on, we want to do that immediately instead of, say, waiting until this index c, and then we can do another subarray somewhere over here. Because what if there's a subarray in the middle between b and c that we're not going to consider because we take c instead of b, right? Taking b immediately instead of waiting until we get to c is always better because it leaves the possibility of subarrays in here. And we're always trying to find the maximum number of subarrays. So we want to be greedy and take these subarrays as soon as possible. So that being said, the catch that I mentioned earlier is that if we take a subarray, we can no longer use any of the elements before. So say we're at this index b, we find a prefix sum that's equal to b minus target over here, and we're going to take this subarray as part of our answer. We're not going to be able to consider any of the values before b anymore. So this is all going to be out. And why? Well, that's because if there were any subarrays in here that we could have used, we would have used those already because of the greedy, right? We're going to consider taking the current possible subarrays before waiting for future ones. So any possible subarrays in here were already counted. And since we've already counted those, and we've counted the one that includes b, we're going to wipe out all of this. So all of this is going to be gone, and then we can only start considering prefix sums from here. And the prefix sums are just going to be normal because prefix sums are just going to help you determine what the sum of a subarray is. It doesn't actually contain any information about what indices you have used and haven't used. So yeah, that's our approach. We keep a set of the prefixes we've seen so far, prefix sums we've seen so far, and then we update it. We update our current prefix sum. If s minus target has appeared in the ones we've seen previously, then we want to increment our answer because that gives us one extra subarray. But also we want to revert prefixes back to an empty set because we can't use any of the prefixes like that have happened before. But that being said, we also want to add the current one because even though we can't consider any of the elements before, the prefix sum of b is only going to be used when we're counting b plus 1 because subarrays, like, it's an off by one thing. You don't have to worry too much about it. So we basically are allowed to use the prefix sum of our current index even if our current index has already done a subarray. Okay, that's a little bit confusing. You don't need to worry about that. So the code is pretty simple. I hope my explanation was too. Yeah, this is kind of similar to two-sum, but you also have to use a greedy algorithm. Problem 3, minimum cost to cut a stick. Okay, this is the problem that got me super excited, right? So here's why. I'll read it. Problem 4, minimum cost to cut a stick. Given a wooden stick of length n units, the stick is labeled from 0 to n. Given an integer array cuts, where cuts I denotes a position you should perform a cut at. You should perform the cuts in order. You can change the order of the cuts as you wish. The cost of one cut is the length of the stick to be cut, and the total cost is the sum of the costs of all cuts. When you cut a stick, it's split into two smaller sticks, and yeah, okay, so look at this example. It's a stick of length 7, cuts are at 3, 5, 1, and 4, and it shows that when we cut 3, we're going to add a cost of 7 because the stick that was cut had length 7. When we're cutting this one, for example, we're cutting at position 1. This stick is of length 3, so we add 3. When we're cutting this 4, we add 4 because the stick it was cut is of length 4. And yeah, we just continue on. Yeah, minimum cost for this would be 16. And the next one, minimum cost would be 22. Okay, so originally I was thinking of some smart greedy thing, but it didn't actually work, like, because it was just wrong. I couldn't actually prove it to myself either. And then I tried like a recursion solution. Yeah, this is the remnants of my greedy one. So recursion solution, it basically considers all the cuts you can make and then takes the best of those. Well, okay, each cut produces 2 sticks, so you're going to consider each cut you can make, take the minimum cost of cutting those 2 sticks further. And this recursion is going to be exponential, but we can reduce that. Like normally when you see something, like when you see recursion and it doesn't have very many parameters, like this one only takes 2. Actually it takes 3, but that was the remnants of my greedy solution. Okay, so yeah, it takes 2 parameters, left and right, because that's the section of the stick, the original stick that you're going to cut. It only takes 2 parameters, and when you see a recursion that takes a very small number of parameters, like 1, 2, or maybe 3, you can probably make a dynamic programming top-down out of that. You can make a top-down DP out of that. In Python, you can use this thing called LRU cache. I don't know, whatever. So you can use this thing called LRU cache, and it basically caches functions and does the job of a DP table. But I did dumb stuff with greedy, and I include 2 extra parameters. And this was like in the last 2 minutes. So I was like, whatever, let's just use a DP table that we code ourselves. So I made a DP table, used memoization over here, and then it worked. Yeah, it just did. So lesson to be learned here is that when you have a recursion that takes a very small number of parameters, 1, 2, or 3, you can almost always memoize it and make it into a top-down DP problem, and that's going to solve your TLE problems. Yeah. Okay. Cool. So I think that's all the problems in Leetcode Contest 201, and I hope these explanations were helpful, and I hope you learned something. And yeah, Well, thanks for watching, and I'll see you next time. Goodbye.